Okay, so this video is about electromagnetism. I mean, a few problems that you might have. But in the last video, I forgot this one here. So here you have, so you can pause the video again. So you have capacitors in series. So if the capacitors are in series, the equation is the opposite uh, than the equation for the resistances. So it means if the resistors are in series, to find the equivalent resistance, you need to apply the equation. Um, you need to apply the equation 1 over C1 plus 1 over C2 equals the equivalent 1. So if you have two of them in series, right, that will be something like this. So the equivalent will be half. So it will be half as great. Okay, so let's move to electromagnetism, but easy questions, very simple questions. I think we did. Okay, so this question here with an application in biology, ATP, biological system. So they are talking about the electric potential energy. So don't think too much about the biochemistry here. Just think physics right away. So it says, so they talk about the electric potential energy. Okay, so electric potential energy between two charges. The equation, you have a constant here, so it's proportional like Q1 proportional like Q2 over, and here it's inversely proportional to the distance between the two charges. So it's a potential energy, so it depends on the configuration of the system. Okay, so the position of the charges relative to each other. And here it's a negative. It's a negative electric potential, which means if you want to separate the charges, you will have to do work. So anyway, so if you multiply the distance by 2, so if this is divided by 2, what's going to happen to the electric potential energy? So if this is multiplied by 2, so this one has to be divided by 2. So the electric potential energy will decrease by a factor of 2, not 4. Okay, not to confuse with the electric force, which is Q1, Q2, and the distance square. Okay, so then you have this question. So this is the question about using the right hand rule. Okay, so here we have a negative charge particle and it's going counterclockwise. So it means it's going this way. So if you take that point here, okay, so it's a negative charge, so minus Q. So if you take that point here, it means the velocity is this way. And the force, if it's going into a circle, so that means there is a centripetal force. That force here, it's the magnetic force, is perpendicular to the velocity in toward the center, okay, of the circle. So it's a centripetal force. So the magnetic field has to go into the page or out of the page. So you have to use the right hand rule, except that in that case, because the charge is negative, you can use the left hand instead. So if V is to the left and V is to the left, F and V is to the left, and you want F to be down. So then you need B to be towards you. Okay, so you can use your your left hand. Use your left hand because it's a negative charge. So V is to the left, then F is down. So B has to be towards you. So the answer is out of the page. In the page will means across, but this is out of the page. Okay, so let's go to the next one. So capacitor. So for a capacitor to work, you need some insulator between the plates, right? So it means you have a plate here, plate. So this one is charged positively. This one is charged negatively here. And then you need between them, you don't want them to be combined. So between them, you need the insulation. The insulation, this is not an insulator, this is not an insulator, this is not an insulator. So that will be the only equation that is possible. Okay. The next one. So here they talk about potential. You want to know where the electric potential, electric dipole, you want to know where is the electric potential 0. So this is a electric potential here. So you have a plus and a minus, right? So it goes out of the plus into the minus, out of the plus into the minus. So that will be for the electric field, right? Not for the potential. So that will be the electric field. So it's always inside the minus, and here it's going to be outside the plus. And the electric potential, so here you have a bisector here, and you see the electric potential has to be always perpendicular. So here it's like you have a little hill, and here you have a little valley. So it's going to be inside. So the electric potential, it's going to be using the superposition method. So it will be from the positive charge, so K, and the distance R1 from here, and minus from the negative charge at a given point. So that will be the electric potential at a given point. And we take the electric potential to be 0 very far away at infinity. Okay, R2. And you want that to be equals to 0. So in that case, you want, so you take the point here, that will be R1, that will be R2, and we can find the electric potential here. So for that to be 0, you need to have R1 equals R2. So it means here, for example, the only place this is possible, the distance R1 equals R2 will be on that line. So the answer will be at all the points on the line, passing through its center. So, okay, so the answer is B. B will be the answer. Okay, so next one, you have an electron. An electric potential V, the electric potential increased to 4V. what's the final speed? Okay, so you have an electric potential. Okay, let's say you have something like this, and you have let's say this is minus, this is plus, and here you have an electron. You place it here, and it's gonna accelerate across a potential V. So the definition of the potential is the energy per unit charge. So the potential like from the power supply, is the electric potential energy per unit charge. Okay. So the potential energy is the charge times the potential. Okay, so if you multiply the potential by 4, so the electric potential will be multiplied by 4. Okay, so that potential energy that it has, right? It's going to lose it, and it's going to turn into kinetic energy. So I'm supposing here that here it starts from rest. Okay, so all that potential energy turn into kinetic energy. So if this is multiplied by 4, the kinetic energy here is multiplied by 4, so the mass does not change. So it means the speed squared is going to be multiplied by 4. So the velocity will be multiplied by 2. So by what factor is the electron final speed greater in the second experiment compared to the first? It will be greater by a factor of 2. So the answer is D. Okay, so the voltage is the potential energy per unit charge. If the potential energy here is multiplied by 4, kinetic energy is multiplied by 4. Kinetic energy depends on the speed square, so the speed is multiplied by 2. Okay, so this is the definition of voltage again. So the voltage is the energy per unit charge. So for 1 coulomb. Okay, so when you have a 9-volt battery, that means 9 joule for 1 coulomb. By definition, that's the definition of a voltage. So if you have 2 coulomb, that will be 9 times 2, which is 18 joule. So the answer is C. Okay, so this one, okay, so this one is with the magnetic field. So let's look at what's going on. And again, you should pause the video. So you have a current, let's say current I. So if you have a current I, you have a magnetic field, right? So the magnetic field will curve around the current. So it's going to be very close, very strong, close to the wire. And here it's going to be weaker. So the magnetic field, okay, is proportional to the current and inversely proportional to the distance where I'm looking. So anyway, the magnetic field will be a vector here, So if I take it here at that point, so you see we have the magnetic field here, it's a vector, it's going around. So at that point here, B will be in the blackboard. Okay, it's going in the blackboard. So that will be at a distance R. And then it says, and B has a magnitude of 10T. And you can take your right hand. So if the thumb is the current, so going up, with the right hand, you see that the magnetic field is going into the board. And then you have another current here. So it's the same distance. So that's point P. That here, it's your distance R. So that will be the distance R. And the current is twice. So the current is twice, is it? It's twice the current, but going in the opposite direction. Okay. So the magnetic field from this here, you see it's circling around. So you take your right hand and you see that the magnetic field here is also going into the blackboard. So into the blackboard from here. So this is 1, this is 2, this is 2, and this is 1. So both of them are going into the blackboard, so they're reinforcing each other. This one has twice the current. The magnetic field will be 20 Tesla. So the total will be, so this is B2, this is B1, so it will be 10 plus 20. It's going to be 30 Tesla. Okay, so you can look back at my playlist. So 30 Tesla. So maybe this one was a little bit tricky. And that's the last one. So this one is the last one. It's a little bit challenging. So there was a negative charge here, and you grab the charge and you move the charge here along that line. So let's say you are moving at a constant speed and you have two positive charges on both sides. So the work done is the change in electric potential energy. Let's say you are moving at a constant speed here. So at that point, you have a potential. Let's see, you have an electric potential. So that electric potential energy will be Q delta V. So the difference in voltage between this point and that point. So at that point, the voltage will be, it depends, K, and then the distance is the same. So it's going to be 10 for 10 Coulomb, and that distance R. Okay, so that will be the energy per unit charge. But here, at that point, you're going to get exactly the same potential. So here and there, it's like they have the same altitude, they have the same potential. So delta V equals 0, which means there is no change in electric potential energy, which means that the work equals 0. So the work done equals 0. The other way to do it is to look at the force, the electric force, the work that you have to do. The electric force, so you want to look at the work that you are doing, moving this charge from here to there. So on the way here, this charge, which is negative, it wants to go in this direction. Okay, so that will be the electric force. And you have to do negative work. So the work that you are doing is going to be negative. And then when it's going to pass this point here, when it wants to pass this point here, okay, so now it wants to go down, and you are doing positive work. You have to work against the electric field. So the work done, the total work done equals to 0. because the work done from here to there equals to work done from here to there. So the total amount of work equals 0. So that was the answer. And there was another question. I'm gonna keep those questions for next time.